A neural network is built from one tiny part, repeated over and over, the artificial neuron. Master this single piece, and the whole network stops being mysterious. So let's open one neuron up and run it on real numbers, with nothing left to guess. So what is a neuron, really? At heart, it is a tiny decision maker. It takes in a few numbers, weighs how much each one should matter, and combines them into a single output. Think of deciding whether to head outside. The temperature matters a lot. A small chance of rain matters less. A neuron does exactly that kind of weighing, just with numbers and simple arithmetic. Here's our neuron, sitting in the middle. Two inputs feed into it from the left. The first input, x1, is 2.0. The second, x2, is 1.0. Think of them as two measurements describing a single example. Every connection into the neuron carries a weight, and the weight decides how much that input counts. Our first weight is 0.6. It's positive, so this input pushes the result up. The second weight is minus 0.4. It's negative, so this input pulls the result down. Here's the key idea. Training a neuron simply means searching for good weights. The first thing the neuron does is multiply each input by its weight. Watch the top input travel down its connection and get scaled on the way in. 0.6 times 2.0 counts up to 1.2. And on the bottom, minus 0.4 times 1.0 gives minus 0.4. Now the neuron gathers those scaled inputs into a single running total. We start the total at 0, add the first product, 1.2, and the total climbs to 1.2. Then add the second product, minus 0.4. Because it's negative, the total drops back down to 0.8. There's one more number to add, the bias. The bias is a value the neuron adds no matter what the inputs are. It shifts the whole result up or down, like setting a starting point before any input arrives. Our bias is 0.2. Add it, and the total lands on exactly 1.0. We call this final sum z. But we can't stop at z. Notice that z can be any number at all, large, small, or negative. And everything we did so far was only multiply and add, which can only ever produce straight lines. To let neurons bend, and to turn z into something we can read as a confidence, we need one more step, a nonlinear squash. That step is called an activation function. The classic one is the sigmoid, this smooth, S-shaped curve. Feed it any number along the bottom axis, and it hands back a value between 0 and 1. Big positive numbers come out close to 1. Big negative numbers come out close to 0. And 0 lands right in the middle, at 1/2. So let's push our z through the curve. Find z equals 1.0 along the bottom. Go straight up until we meet the curve, then read across to the left axis. The output counts up to 0.73. Two inputs went in, one clean number came out. And that single number is the neuron's answer. Because the sigmoid always lives between 0 and 1, we can read 0.73 as a confidence. Here, the neuron is leaning fairly strongly toward yes. Closer to 1 would mean more sure. Closer to 0 would mean leaning the other way. So which parts actually change when a network learns? The weights and the bias are the knobs. Those are tuned from data, over and over, until the answers get good. The activation is a fixed shape we choose in advance. It does not change. Everything else is just multiply, add, and squash. In PyTorch, this is refreshingly short. A single linear layer holds the weights and the bias and does the multiply and add for you. Then one call to sigmoid applies the squash. 2 numbers in, 1 number out, the exact neuron we just built by hand. So here's the whole neuron in 3 moves. Multiply each input by its weight, sum them and add the bias to get z, then squash z with an activation to get the output. That's the entire building block of a neural network. Next, we'll wire many of these neurons together into layers.